maximum average power transfer. This, as I mentioned, is related to the Thevenin or Norton equivalent circuits that we did back in chapter 4. Right. And with maximum average power transfer, we're looking to figure out what the impedance of the load should be to get the most power we can out of our source, our linear circuit, which is our Thevenin equivalent circuit, a voltage supply in series with an impedance now, that will allow us to get as much power as possible transferred into our load impedance. Right? So, why is this type of thing important? This is really important, in fact, in AC circuits, because in AC circuits, our impedance is often dependent on frequencies, right? So we have to not only match a resistor, like we did in DC, but now, really, we need to match the reactance, which is frequency dependent. So once we know what frequency we're operating at, we need to calculate the impedance at that frequency to make sure that as close as possible we are able to match our load impedance to our Thevenin impedance to get maximum power transfer. With oscillating signals, there's another piece of this that we don't really talk about for this class, but when you send a wave, a sinusoid, down a wire, for example, it will hit any changes, like where you actually attach this impedance. It will see that impedance kind of like light bouncing off of a wall or a mirror. And so if the impedances match, it's like when you look at like a fish tank or something, right? And if you look at it right, and if the water matches the glass pretty well, you just see right in and it looks super clear. Or like on a really clear day with a really clear piece of glass, if you catch it right, it looks like you just see right through. You see no reflection, right? Kind of like that, right? If you can match things perfectly, you just go right through. If you don't, you'll actually get a reflection, right? So that reflection can come back, and it can actually cause damage. Because remember that idea of interfering waves? We said if two sinusoids line up on top of each other, they actually double in height. So if a signal is going down a wire and it reflects back up the wire and they match up perfectly, you can actually double the height of the voltage. I actually had an experience with this that was really bad, and it happens more than people would probably like it to, but a piece of equipment that I was working on, I worked with. It didn't happen to me, it wasn't my fault. But it happened to a piece of equipment that I used on a somewhat regular basis. And so this was something called an Asher. It uses a radio frequency plasma to clean gunk, if you will, to clean organic stuff off of silicon wafers when you're trying to make semiconductor chips, right? So this Asher operates at about 13 megahertz. Pretty high frequency, right? Well, one of the connectors had gotten a little bit bad in the back. And so that connector, it's supposed to match the generator that's creating the frequency, right? Like the source, to the actual plasma head, so that the power all flows from the source through the plasma head and into your chamber, right? Well, that needs to match really, really well so that I don't get those reflections back. Because this thing pumped out about 500 watts of power. That's pretty powerful, right? And you're putting it down a little wire, So there was a fray in the wire. It was slightly damaged. It had been bent or something, and it had kind of bent and damaged that wire a little bit. And one day the cooling water went down, and someone was using this machine. And so when they started using this machine, suddenly that little fray caused a reflection because it no longer matched impedances, because they had changed the impedance just by bending that wire a little too much. And so all of the power they were trying to send into the load resistance, the load impedance, a piece of that reflected back and doubled the voltage, or increased the voltage. So now the 500 watts that was supposed to be going in, some significant fraction of that came back, so now there was more than 500 watts flowing through the cable. It was only designed to carry 500 watts. There was no cooling water flowing at that moment. It had been okay because the cooling water kept the heat down, but guess what? The cooling water went down, and it fried the source, because this thing shot up in power much higher than it was supposed to, nowhere for that heat to go, and it melted. $10,000 repair, right? Because of a cable getting bent. That was it, right? And it fried the generator. So simple things, right, they can actually make a big difference. We talked about like doing this maximum power transfer idea with speakers in your car or in your house, that you want to match the impedance of your speaker to the impedance of your amplifier. Otherwise, you can blow out your amplifier, right? Because the power from your amplifier can't get out of your amplifier and into your speaker. So where does it go? Turns into heat in the amplifier, and the amplifier pops, right? So this concept, especially with AC, is really important, right? And the same thing applies, though, right? Which we see in the upper right yellow box. The matching impedance is the best impedance to get maximum power transfer, right? In that case, we want to have the load impedance match the Thevenin impedance, which means we need the load resistance, the real part, to match the Thevenin resistance, and we need the load reactance to match the Thevenin reactance, right? Those two pieces. So if that is the case, right? So actually we don't want the load reactance. Maximum power happens, in fact, when the load reactance is 180 degrees different from the Thevenin reactance. Again, because you want to normally use complex conjugates when you're doing two impedances for power. We'll see that a little more in a second. But if you remember, with the Thevenin equivalent, we had we said that P max. Let's switch to a better marker here. We had said that P max was the VTH squared over 4 RL or RTH when RL equals RTH, right? It matched this, right? This was the expression we had. Now, you'll notice that the maximum power transfer is slightly different, right? For AC, this is for the DC case. For the AC case, because we're dealing with impedances and real and reactive, we actually deal with the maximum power being magnitude of VTH squared divided by 8 RTH. Where is the 8 coming from? Well, if you remember in our power expression we just had, there was a 1/2 out front. So when we dealt in DC, power was V times I. But that's because it was all constant. Now, sort of half of it is constant, and the other half is oscillating up and down. So we take that constant part, right, that has that extra half in it, and that half yields the 8 on the bottom, right? And when we're doing the VTH here, it's a magnitude squared, and so that's why we want to have, ideally, the complex conjugate so that the reactance has a minus sign. Because when you do magnitude squared, you want to be able to do complex conjugates. So that works out pretty well. Again, if we have a matching impedance with real and reactive parts, great. But a lot of times we don't actually want to add in a reactive impedance, right? Sometimes we want to match as best we can with just a resistor. And in that case, then our best bet is to find a resistor that has a value equal to the magnitude of our impedance. So rather than just looking at the resistive portion of the Thevenin impedance, if you're going to try to match with a full resistor, with a pure resistor, and your regular or original impedance is complex, the best thing you can do is to match it to the magnitude of your impedance. And you'll see that if it's real, XTH is 0, And this matches. RL matches RTH, right? So this is one piece that's a little bit different than what we saw before, right? We did never have to deal with matching with something that wasn't the same resistor. Now we can do it either with a fully complex impedance or with a purely resistive impedance. Right? So calculating it isn't very difficult, right? Because we already know how to find the voltages and the impedances. So we're just going to go through our circuit. Right? So we're being asked to find the load impedance in ZL, right, that will absorb the maximum average power, and then calculate that maximum average power. So I have to find the Thevenin equivalent of this left half of the circuit. So what is the Thevenin equivalent of the circuit as seen by the load impedance, right? So if I look at this, I want to find VTH at this point, and I want to find ZEQ or ZTH of this side, right? So let's start with the initially finding out the ZTH. So because that's the one I really, that's what's going to tell me my matching ZL. So ZTH is turn off the source. That's an open circuit. And then I have the 8 ohms, the negative J4, and the J10 in series, and that's all in parallel with the 5, right? So ZTH is 5 plus, 5 in parallel with 8, and then plus J10 minus J4, so that's going to be plus J6. That's going to be my impedance.
Impedance values in multisim?
Can I add them?
Like, could you put a capacitor in and give it an impedance value instead of like a capacitance value?
Oh, in multisim? No, you can't. You have to actually give it a true capacitance. And so the best way to do that in multisim is to just choose a frequency that you want to work at.
Yeah.
And so you could just assume omega is 1 or something like that, or 10 or whatever you want, and just use a capacitance value that's related to that. So if I wanted to try to put this circuit in, I might just assume omega equals 1, and then so I would solve, and I would say, well, okay, if the impedance of my capacitor is negative J4, well, that expression is 1 over J omega C, and if omega is 1, it's gone.
I got you.
And now I can just solve for C. So unfortunately, you do have to do a little bit of math. It's a little simpler on the inductor because it's just J omega L. So if I assume omega is 1, then L is 10, right? But with the capacitance, you've got to flip it over. So yeah, but so you can do it. So you certainly should try that on 1 or 2 problems. So because again, multisim is a great way to check your work, right? So in this case, once I work this out, right? I could put this into Matlab. In fact, I left my Matlab running this time. Just to remind everybody. So if I wanted to do this, I could say, all right, ZTH, I want to have 5 in parallel with 8 plus J6. I'm going to use my little parallel command, right? So ZTH equals parallel combination. It's a function with a matrix as an argument. Ah, come on. Oh my gosh, you don't need to give me all this stuff. I don't know how to turn off the notifications on it. All right. How do I turn off the notifications? Come on. Oh my gosh, it's going crazy on me. Okay, I know. Oh my gosh. Oh, for crying out loud. It's going to be kind of busy right now. Oh, for crying out loud. Why is that other one up there now? Come on. Oh my gosh. I'm sorry. I don't know why I decided to go crazy all of a sudden. Whatever. Okay. Anyways, back on track, I guess. So I want to have my two elements be 5, right? And 8 plus J6. So I'm going to put that inside of parentheses. And if you do 6J sorry, Matlab, I mean, we'll understand it. Why is it not, is it waiting for it? All right, and so we have 3.416. Plus 0.732J. So the best matching impedance is the complex conjugate of that. So here I have the Thevenin impedance being plus 0.737. So the load impedance that I want would be 3.416, the same real part, but minus 0.732J. And this is measured in ohms, right? It's an impedance. Okay. And then I can find the maximum power transfer. I need to know VTH. So how do I find VTH? Use whatever method you like to find the voltage at this point, right? Assuming ZL is not there. So the open circuit voltage. So the voltage at this point, I could do current division, or you could do a little mesh analysis. Well, you'd have to do a combination of a loop and a node, or a little KCL, right, at the 3 points. I don't know. Pick your method, right, that you like the best. Let's do this with some current division this time. All right. So I'm going to divide the 2 amps. Some flows to the left, some flows to the right. I want to know the current flowing in this right-hand branch. And so that's going to be I in the right is going to be equal to, and this is 8 minus J4 divided by 8 minus J4 plus 5 plus J10 times my input current, 2. Right? And then when this is, once I know this current, the voltage across the 5 ohm resistor is just IR, right? So if I wanted to turn this into voltage, I would just take this, I would multiply it by R, and I'll get the final, the 5 ohms, which is equal, right? And I'll get the final VTH. Right? So again, I would do this in Matlab. So RZL is equal to ZTH prime. That's how you get the complex conjugate in Matlab. Okay, you can just use the little apostrophe symbol. And then let's see. So I want to find IR, right? I can just put this all in together. Actually, VTH is going to be equal to. Let me be careful typing this all in, right? I have a numerator, which is 8 minus 4J divided by, and again, my denominator is, and there's 2 pieces of it added together, right? And so I'm going to make sure I have the right parentheses in place. 8 minus 4J and 5 plus 10J. Right? Now that whole thing has to be multiplied by 2, So again, if I want, I can put that whole thing in parentheses, or I could put it into the numerator piece. So for now, I'm just going to say that's my multiplication factor, like I have it written here, times, now that's all in parentheses, times 2 amps. And then I'm going to go ahead and put it into the voltage by multiplying by the 5. The 5 ohm resistor. And that should be my Thevenin voltage. Okay, 3.9 minus 4.8 J. J. Maximum power transfer. VTH magnitude squared divided by 8. Oh, this is the maximum average power transfer, right? So it's 8 RTH. So the resistance part of my equivalent impedance. So I want ZTH magnitude squared. So I can do that by taking, so Pmax equals, right, VTH times VTH prime. That's how you do a square of complex numbers, usually, right, when it says magnitude, right? It's the number times its complex conjugate